Thank you very much. First of all, I'd like to thank the organizers for the invitation and for all their efforts to make this event possible. It's really fantastic to be here. Today, I will overview some works realized with my colleagues, Ralph Penser and Gleb Oshanin, on extreme statistics of the fastest first passage time. Good. So this is the outline of my talk. I will start with a short introduction to the conventional setting of fastest first passage times for diffusive search. Yesterday, I've heard many talks on them. In particular, Sean Lawley gave a very nice presentation, so I can go faster on this part. And then I will discuss three different scenarios which were less studied in the past and which can give some different results. And at the very end, again, I will question to which extent these extremal results are applicable in biology, and we can discuss at this point. Okay, by the way, if you're interested in target search problems, I can advertise the book that I credited with Ralph and Gleb Oshanin. I have many examples and models of this phenomena. Okay, so let's start. And I will start with a very basic example. So just Brownian motion on a half line. It starts from a point x naught, and we would like to find the first time when it hits the level 0, which could be a target. And so this is a random variable, which can be characterized by the survival probability, which satisfies itself diffusion equations that you can solve, and at the end you get very simple results for this one-dimensional example. That's fine. Now we would like to see what happens if you have n particles which search for the target in parallel. And in that case, we're interested in the fastest first passage time, so the minimum of these n identical variables. And by the way, throughout this talk, I will always focus on independent searchers, so it always be independent random variables. And in that case, the problem is essentially solved in one line. So if you know the survival probability for a single particle, then you can just take the nth power of the survival probability and you're done. And to some extent, I can stop here and sit because this is the law for this random variable. You cannot go do better in some sense. You have all information you need. Well, still we do some efforts because we want to understand how the properties of this random variable scale with the number of searchers. And in particular, we can consider the mean fastest first passage time, which is obtained just by integrating this variable. And we would like to know how it depends on the number of particles. And let me first give you very hand-waving arguments. I'm a physicist, so let's just draw this survival probability. It's a function from 1 to 0. And if you put it to the power n and you start to increase n, you see that you start to attenuate more and more this function. And so the contribution to this integral essentially comes from the vicinity of 0. So what really matters here is the short time asymptotic behavior. You know the solution explicitly. You can put it here, do some basic analysis, and then you come with this famous expression 1 over log n behavior, which was predicted 40 years ago. Well, from my personal point of view, this result is very pessimistic if you think in terms of the optimization. Because if your goal is to reduce the fastest mean first passage time, you need to deploy a huge number of particles because of this logarithmic dependence. And I will come back to this point during my talk a number of times. And I would like to make another comment here that you see, to get this extremal statistics, you really need to know the survival probability, or at least its short time behavior. So the mean first passage time for a single particle is not enough. And unfortunately, in our field, there is still a lot of focus on the mean value. And if you want to go to something more interesting, you need to go beyond the mean value. So please don't stop on the mean when you can do. Okay, if you dislike these very hand-waving arguments, then you can look on Sean's papers. There are many of them. I just cite a few of them here, who gave exhaustive description of fastest first passage time on a mathematical level of rigor. So in particular, well, I will just mention one result that I will use in the following. He proved that if the survival probability approach unity with this functional form, which covers many practical situations, then the minimum appropriately scaled converged to Gumbel law, and also Sean computed the asymptotic behavior of all these parameters, We found the mean values, the variance, the joint distributions. There are a lot of results, so I encourage you to look at these papers. Now, my interest is more on the applicative side. So this result is a rigorous mathematical result, so we cannot argue about that. But is this result applicable? And here's a problem where it can be applicable. There are many situations in biology where many searchers are deployed to find something. I will give you just three examples, three illustrations. So for instance, if we speak about neuron signaling, a release of a single vesicle with neurotransmitters gives few thousands of neurotransmitters released in the cleft, and only one is sufficient to find the receptor on the other neuron and to pass the signal. In the same field, once the activation potential arrives, there are calcium ion channels opened, and then there are tens of thousands of calcium ions which enter the dendritic spine, and again, only few of them are enough to make pass the signal. And the most famous example is the case of sperm cells. There are up to 300 million of sperm cells released, and only one needs to find the target. And there is a big question in biology, so why you have such an extended number of searchers? Because to have them, it has a biological cost. You have to produce them or to maintain them, so there should be some reason for that. And there is this famous paper by David Holkman and his colleagues who suggested that maybe this results, so this slow improvement of the mean fastest passage time with a number of particles, can explain why you have so many searchers to be used. And so one of the motivations for this work is to try to answer the question, is this behavior really applicable in biology? Quite similar to what Sean discussed yesterday. So with this introduction, so let me consider three different situations. I would like to emphasize that on this example I discussed before, we focused on a classical setting when you have all particles start from the same point at the same time. And I would like to consider different situations. First, what would be the effect of distributed starting times, effect of distributed starting points, and then what changes if you change the model of displacement. And at the very end, I will come back to the question for applications in biology. So to discuss the effect of distributed starting point, let me come back again to the example of calcium ions. So when an ion channel is opened, you see that the calcium ions go one by one through the channel. So it means that when the first ion enters and starts searching for the target, all the others are still outside. So in that sense, you need to take into account this extended injection of particles to account for the whole effect. And so this extended injection can be just a constant profile, for it's open for some time, or it can be any profile you'd like to consider. In particular, the kinetics of transmission through the channel is quite sophisticated, so it's not just a constant function, so it's more complicated. So you can account for that. So in this setting, what you have still the first passage time for each particle, but each particle now starts with an entrance time delta k. And finding the target now is delta k plus tau k. So the extremal statistics would be just the minimum of these sums. And if all the particles move independently, again, the minimum is described as a product of survival probabilities for individual particles, but this time is delayed by this times delta k. And in the paper, we consider two scenarios. Well, the first is deterministic injection. So suppose you have your profile, you separate it in small intervals, and at each interval, you inject a fraction of particles. That's kind of quite natural representation of what is the dynamics and injection dynamics is. But there is an alternative way to look at this problem. It's random injection. So you can consider delta k as also random variables, which are drawn independently from a probability density psi of t. And so, well, you can solve this problem. Actually, it's quite simple. You can show that the survival probability for the extremal statistics is again nth power of some averaged survival probability for a single particle. And for this one, you can compute it. So for instance, if you have a random injection, you have just sum of two independent random variables. So the cumulative distribution of them, it's explicitly written in terms of sort of convolution between the profile and the survival probability for one. And in the deterministic case, you can also do a computation. It's a little bit more complicated, but still it has a structure of convolution between these two objects. And once you have these formulas, you can look again at the mean fastest first passage time and see how it depends on the number of n. So to proceed, we again assume Brownian dynamics. So we use again these asymptotic relations. And also we assume a quite generic form of the profile. As you can anticipate, what matters is the short time behavior. So we specify what happens at short times. And then you substitute these two asymptotic results into these relations. You do some asymptotic analysis. It's quite technical, but at the end, you can show that the average survival probability inherits this dependence from these two, but with new parameters, which are these bars, which are, of course, related to the old ones. There are explicit relations you can find in the paper. And so, as a consequence, we come to the mean fastest first passage time, which again indicates 1 over log of n. This time it can be in some power, which depends on the profile of the entrance profile. Okay, so let me give you an example how it works. Again, for Brownian case in a half line, I took the gamma distribution profile for the injection. So you have a nu is a shape parameter, so it determines which shape do you have. So for instance, nu equal 1 is just an exponential decay. And so here you would recover this dynamic redundancy that was presented yesterday. But you can also consider different cases of nu, which would represent kind of more bounded profile, like the profile which starts with non-zero value here. And of course, this is just an example which enters to the family of profiles that we consider it. And this is the result. So let me comment on different curves you can see here. Well, first, the blue curve is the exact solution for the random injection profile. Circles are Monte Carlo simulations just to check that we didn't mess up with the computation. So it fits quite well. And so let me compare this exact result with other curves. Well, first of all, we can compare with the instant injection. So this gray curve here. So we inject the same number of particles, but instantaneously. And in that case, well, the effect is quite expected. You have just a delay. So the extended profile appears slower at longer times. It's shifted to longer times as compared to the instantaneous one. But this delay, well, here it's just maybe a factor 2 or 3, but it can be orders of magnitude different depending on the injection profile you use. So if you want to apply these extremal statistics to experiment, if you have an extended delay, you have to take it into account. Another comparison, the blue curve and the red curve. The red curve corresponds to the exact solution for the deterministic injection. And you can see that they're almost identical. And in the paper, we prove that they should be very close in the large n limit. So it means that these two scenarios, they are equivalent in the large number of particles. The deterministic one is more natural when you think about how the particles progressively enter the system, but the random one is easier to deal with and to do all the computations. And maybe the most important part is the comparison with the green curve. So the green curve is the asymptotic Gumbel distribution, which was obtained by using, again, the 1000 particles. And you see that here it's quite different from what we have here. When n goes to infinity, we must have Gumbel, so that there is no choice. Again, it's a mathematical result. But at finite n, and for most practical results, you will deal with finite n, which may be not so big, you see that you have a difference which can be quite significant. So let me just try to understand where does it come from. So it's the same result as before. And now I show what happens for the instantaneous profile. Again, the same number of particles, and you can see that the Gumbel distribution is much closer to what we get for 1000 particles. And so let's try to think what is different between this and this case. And from the asymptotic points of view, you have the same type of the asymptotics. The only difference is the scaling exponent here. Well, for Brownian motion, just 1/2. And for extended profile, it's 1/2 plus this exponent which comes from the profile. And so what we observe empirically, it's not theorem, it's not even mathematics, it's just for larger alpha exponent, we get slower convergence to the Gamow distribution. And here it's a practical question to the audience. I think really if we want to use these asymptotic results, we need to come up with some approximation. So some approximation which would be valid or accurate at moderate values of n. So I hope that someone in the audience can do it, and that would be very useful in practice. Okay, now let me move to the next point, another scenario, and to see the effect of the distributed starting points. Again, I will start with an example. So in this case, we started from a fixed starting point. And now suppose that instead of fixing x0, we will take starting points uniformly distributed on the interval from 0 to L. And so x0 would be itself a random variable. Then what you do, just average over this random variable, you get this average survival probability. Well, in this particular example, you can compute it explicitly. And then you take the asymptotic behavior at short time, and you get this square root t approach, which is very different from what we had before. You don't have this exponential factor, which makes a very rapid decay to 0. And as a consequence, the mean fastest of passage time decays 1 over n squared. So here you have a tremendous improvement in efficiency as compared to 1 over n log n behavior. So that was just an example. In the paper, we consider it general bounded domains. Some targets can be on the boundary or in the bulk. It's just illustration for 10 and 100 particles. And then what you have to do again, you can compute the survival probability averaged over the starting point. And then you use the heat content asymptotics, which are quite well developed for this problem. And you get that if your target is perfectly absorbing with Dirichlet condition, then you recover the square root behavior in a general case. And as a consequence, you have 1 over n square decrease. And if your target is just partially absorbing, so you put Robin boundary condition, then you have this linear approach to unity. And in that case, you get 1 over n behavior. By the way, from a practical point of view, this behavior is the most intuitive. You double the number of searchers, you halve the mean first passage time. Well, unfortunately, it's not always like that, and you may have more complicated situations in practice. Now let me move to the last topic, and here will be most overlap with Sean's talk, but well, I decided not to change it from yesterday. So already Sean explained that we use the Gaussian noise when we speak about diffusion, and the physical inconvenience of this model is that at short time, you can go very far away. It's extremely improbable, but this event, the probability of this event will dominate the extremal statistics. And so to check this effect, what we consider is this dichotomous noise or random tumble model in one dimension. So we have a noise which takes just two values, plus v minus v, over random time intervals drawn from exponential waiting time distributions. And so here you get exponentially correlated noises. And the advantage of this model is that it's explicitly solvable. So you can actually look and check how things works for this model. So in particular, you can just compute explicitly the survival probability for this model. And then you can put it into the previous formulas and you can get the mean fastest first passage time, and you get exact solution for this problem. It's not nicely looking, it's double integral, but still it's completely explicit and exact. And so the first observation that you have here is this T0 bound, lower bound for the mean fastest first passage time. It's just a minimal ballistic time. So if your target is x0 distance away, if you go on constant speed v, so this is the time you need to go. And it doesn't matter if you have one particle or million particle, it's the minimum that you have to spend. But of course, what is more interesting here is that you have extra, the excess factor, which we have here, which depends only on the number of particles and on this dimensionless ballistic time. And so you can analyze the asymptotic behavior of this integral. And what we found that there is this critical number of particles, which splits the dependence on two asymptotic regimes. So if n is much smaller than this n psi, but still larger than 1, we recover this 1 over log n behavior. But we found a different numerical prefactor, 1 over pi instead of 1 over 4. From a practical point of view, it may look as a minor technical detail, but actually it reflects that there is two limits which are not commuting. So I think that this is more subtle difference that one could expect at the beginning. But on the other hand, if n is much larger than n psi, then you get this exponential approach, exponential decay. And quite amazingly, you have the same law which goes from extremely slow improvement to extremely fast improvement. 1 over log n, it may be the slowest you can think about. Exponential is fastest that in practice you can think about. Of course, you can cook up other functions, but still, that's the extreme situations. And of course, you can start the transition in between. By the way, I have to say that this long time behavior was studied by Sean 5 years ago on a general model by a different tool. So we were not aware of this paper, so it was not cited, unfortunately, in our preprint, but of course, we will cite it up in revision. So, and another important point that actually which regime you would have, it depends on the system. So it depends on this dimensionless variable, which for small particles in aqueous solution can be large. And so you would essentially come to this regime as you would expect. But for large particles or large objects like bacteria or sperm cells, this parameter could be actually quite small. It can be like 5. And in that case, you wouldn't never see this behavior. You would see always something like that. So in that sense, the answer depends on the physical system or biological system you're looking at. Okay, well, we also looked on the anomalous diffusion case. So in that case, in fact, what you can do, you can introduce this memory kernel to describe subdiffusion and superdiffusion. That's the model introduced in this paper. And again, we observe that you have first the minimal necessary time and the mean fastest first passage time approach to this limit, while we expect it approach again exponentially if n is large enough. And I would like to mention again that Sean studied another anomalous diffusion case for fractional diffusion equation, and he found a different behavior for this approach. Well, that's all of the story. So instead of making a long conclusion and a summary of the results, let me come back to the question that I raised at the beginning: to which extent this result can be applicable to biology. Again, it's a rigorous mathematical result, no question about that. And we know that diffusion is a universal macroscopic limit of various microscopic dynamics. And I think that the word universal makes things that this relation would also be applicable in biology. But in my opinion, the more important word here is macroscopic. It's only true at long times and long space scales. However, we know that the extremal statistics depend on the short time behavior, which is not universal, and it's really system dependent. And in that case, you may have different situations I presented here, which would have very different dependence on n. And so in that light, it's not immediate application to real system is not granted. You have to really check. And here I can come back again to the question, is the redundancy principle applicable to biological systems? Sean yesterday gave us a positive answer. I, as a physicist, will be more skeptical about that. I think that really we need more work on this field. I think we need to look what happens at short times and how a physical system or biological system you consider depends on the property. What is the right model for this system? So I hope you can find the answer to this question for the next conference, hopefully. And with that, I thank you for your attention.
Questions for Denis? I mean, I would suggest that yes, but there's more applicable. There's like some of these results suggest that it's actually there's more scope for application to biological systems.
It's true. Well, when I said definitely there's a lot to be applied, a lot of results can be applied to biology. My question about essentially about this one overlook and behavior, as I said, from my perspective, it looks very pessimistic if you try to optimize because it's somehow pointless to do that.
That's because, but as you explained, that's because it's from a Dirac initial condition at a single point. And well, if there's two, if there's a distribution, it changes dramatically. If there's insertion,
the question, so if you have a particular like sperm cells dynamics, you can ask whether it's described as a Brownian particles, and I strongly doubt that. So, and then you have to see what is the right model, and maybe we're done because the biological system operates over many constraints. We don't know exactly what it's supposed to minimize or optimize. So it's maybe it's a mean fastest per spatial time, but maybe something else. So I think the speculation here can be quite misleading in some sense. We have to be accurate. That's essentially the very simple conclusion.
Can you talk about where like heterogeneity of searchers might fit into this? Or also, I know there's been some recent work on these like Brownian non-Gaussian searchers where you have.
That's definitely, I think it can lead to other results. Also, the heterogeneity, I think it's in Steed's paper, he studied like 15 years ago, his paper on how heterogeneity, the diversity in diffusion coefficient can affect the search dynamics. So I didn't cite it here, but still, there are many aspects that can affect. As Sean says yesterday, it's really very sensitive. It's short time to very sensitive to everything. So it's non-universal, and then we have to deal with that.
Yeah, I'm curious what types of measurements you think biologists might be able to do to help answer this question. Like what types of details would help? Because I'm very sympathetic, actually, I think, to your answer as well. Yeah.
Very good question. I have to think about. We can discuss. I don't have prepared answers to this.
Let's brainstorm.
I think it's relevant to ask good questions and try to converge on both sides. You can do a lot of models and try to discover from the models what kind of behaviors you had. But if you can also look on the other side from experimental side and kind of clarify something, that would be fantastic.
Can you go back to that slide where you're talking about the approach to the minimum?
This one or previous?
Was it this one? No, one the large N asymptotics of B and yeah.
Okay.
This is like a weird transition. So what's the intuition between? So you need large XC to get N XC to be large. No, you want small.
Let me say, this one is quite natural, and in fact, what Sean showed in this paper is actually much more general. It's not. Well, here we just consider a very simple, explicitly solvable model. He studied a more general situation, and it essentially happens that what he explained yesterday is that if you have many particles, so it's a question of how likely you would avoid the situations that you just go straight away. So in that sense, this limit is much easier, and also if you look on the asymptotic behavior of this integral, it comes immediately. This one is much more complicated. And actually, the fact that it have different prefactors, it shows that there is some subtle points which not totally reduced to standard diffusion.
Makes sense. It's like you hit a wall at some point when your fastest searcher is just going straight there at its maximum possible trajectory, like the optimal trajectory.
Yeah, so if you go
improvement really
straight that you cannot improve anymore, and then this regime tells you, I mean,
adding more,
how likely it's to avoid the situation when you have many of them. It's very unlikely. So this is why you converge very fast. And this is why it's very general, by the way.
This is just a comment as well. And something that I always think about is like, if you look at the first passage time distribution for a single walker, it's very broad. It doesn't even have a mean. Right? The mean's not infinite, whereas the distribution of the first arrival is extremely focused on that mean value. So one of the things even though it might not be accurate, it's saying that, look, it's almost becoming like a deterministic quantity in some sense.
You mean in this case? Or
No,
in
no,
general?
just in general about these extreme statistics, especially for
Well, I think the variance is not as I think the variance goes as log n squared. So in that sense, it still becomes quite broad. And also the limiting distribution is a Gumbel distribution, so it's not kind of focused distribution.
yeah.
Well,
My
because
experience is quite a focused distribution. No,
Sorry?
it is quite a focused distribution.
Yeah, I mean, you have a quite well defined mode. Yeah, this is true. But okay, that's somehow what I mean is that if you have a Gaussian transform, you estimate some variables and then you take more and more samples, your Gaussian converges to a delta function. That would be very focused. For the Gumbel distribution, it converges to some distribution which is still has, say, standard deviation over 1, something like that, divided by mean. But it's a matter of view. So I mean, you can
mean in
be
this
pessimistic
case?
or optimistic.
Here it does, when everything is just going to go
Yeah,
to
in
T
that
naught.
case, it does. It goes very fast. You're right. So in that case, in this regime, it's focused on this value with exponentially fast.
But the variance also goes to zero here.
Variance
right?
goes to zero. You're right. In that case, everything is fine. Yeah, but not for diffusive motion. Right. Right.
Okay, let's thank Dennis again.